Okay, welcome back. So you might ask, why is measurement important? Well, here's an example of why it's really important. In 1999, a $125 million weather satellite that was designed to orbit Mars and take information was destroyed because it flew too close to the planet. And when the researchers were going back trying to work out what had gone on, the engineers from NASA used metric measurements like centimetres and metres, while one of their software contractors used imperial measurements like feet. And so the measurements were wrong. So get your measurements right. Okay, in this lesson, we're going to look at how to generate, collate, and record data. So the things that we're going to look at: primary versus secondary data, raw versus processed data, quantitative data versus qualitative data, discrete data versus continuous data, and different ways to present data. So first of all, primary versus secondary data. The data that you collect as a scientist is generally primary data when you're doing an experiment. And all of this enables us to get information that goes in the results section of our report. So we're looking at the results part of the report and the scientific method. So primary data is collected by the researcher. In many cases, that will be you when you take pH measurements or something in the lab. Secondary data, though, is published by someone else. It could be your textbook, it could be the VCEE data book, but it's other sources of information, which is important that you reference where you get that from. So you want to make sure you're not plagiarising and you're giving credit where it's due. So it must be referenced and acknowledged, which means that you use in-text citations and put a full citation in the reference list. Okay, so some examples of primary data are the volumes that you might obtain if you're doing a titration, or whether you're measuring voltage of a galvanic cell, so you're using instruments or measuring devices. Secondary data, published data that already exists, that might be written in a scientific paper, but the important thing is published, and using the VCEE data book, which is a really important source of information. It's got data on relative atomic masses in the periodic table and E0 values, for example, in the electrochemical series. Now, all data that you're going to use should be recorded in your logbook, because your logbook is your primary source of record keeping and all your thoughts in the scientific process. Sometimes you'll be using secondary data because you can't generate the data yourself. And in some cases, you'll be looking at reputable or credible databases and online sources. And it's important that you can recognise what is reputable or credible. One way of doing that is to use the acronym PRAC, where P stands for precise, R stands for reliable, R is representative as well, A is accurate, A is authoritative, in other words, credible, it's written by someone who's an expert. C is current, so recent time. And the other C is for complete, so information hasn't been left out. So we can use this test to see, is the author an expert? Is the resource current? So was it published in, say, 2000 or 2020? If it's 2020, that's more recent. Is the data complete? Is there anything that's been omitted? And is it representative? And some examples of really good places to look include ChemSpider, which is a UK site, CAS Chemical Safety Library, PubChem, and there's a spectral database for organic compounds that can help you with organic chemistry. There's just some examples of credible sources of information. Then we can have raw data and processed data. And the initial readings that you take are the raw data. So if you're doing a titration, you'll take the initial burette volume and the final burette volume. And these are examples of raw data. You can do the calculation to actually have the tidal volume, which is actually processed data, and you should record all raw and processed data in your logbook. We can further process the trials that we have for a titration into a calculation and that we use in subsequent calculations. And that means that we eliminate any outliers. So for concordant titers, we want them to have a maximum range of 0.10 mil. So we can eliminate titer 15.25 because that's an outlier. It's beyond our acceptable range. We can exclude that. We can use the other three titers and take the average, which means divide by the number of data points, which in this case is 3. And we can then have our processed average concordant titer. All of this data should remain in your logbook, and it's a good idea to date all the information. Also, in the logbook, give an example of the working that you use when you process data. So if you're going to calculate the average concordant data, show an example, a worked example of the working, so that you can see when you go back and look at it, and your teacher can actually see that as well. Okay, next we're going to consider quantitative data versus qualitative data. So quantitative data is derived from the word quantity, which means it's got a value or a number associated with it. Examples include a titer, such as 25.00 mil, or an aliquot in this case, a temperature measurement in 42.1 degrees Celsius, the wavelength of light that might be selected in an analysis, such as 435 nanometers, or a number that we can count, so the number of protons. They're all examples of quantitative data. On the other hand, qualitative data is non-numeric, so it's often descriptive. Just because it doesn't have numbers doesn't mean it's not important. It's very important. It's actually an indicator that helps you recognise if a chemical reaction has taken place. So examples include colour or colour change, the description of shininess or lustre, whether something's dull or shiny, its state, whether it's solid, liquid or gas, whether you see bubbles appear or disappear, and if you see a colour change, note down what the starting colour was and the final colour. So something might start off colourless, but then it might turn light brown. Being really descriptive with your qualitative observations is really important. Record all of that in your logbook. Okay, we can also categorise quantitative data as being continuous or discrete. Continuous data means it can take on any value. And when we're using decimals, that typically means it can be anywhere between 0 and 1. So we could have just a really long number, and we could have 0.10345 if we had an instrument that could measure to 5 decimal places, but it can take on any value. It could be 1 less, it could be 4, or it could be 1 more, it could be 6. So that's what we mean by continuous data. Discrete data, it just means integers. In other words, we can count. A continuous data could be a 25.00 mil aliquot, or if we were doing a titration, it could be 25.05 mil. And that's another piece of continuous data. A mass measurement could be 42.15 grams, or it could be 42.20 grams. So we can see a variation in the number. Number of neutrons is fixed. Every atom has protons and neutrons, apart from hydrogen, and the number of neutrons is an integer number, a whole number. Or if you're doing an experiment and you're doing a number of trials, or you're analysing a number of samples, if you can count them, then that's discrete data. So having, say, 5 samples. And quantities such as mass, volume and temperature and time are all examples of continuous variables. Okay, once we've got our data, there's lots of different ways to present it. And remember, one of the aims of these key science skills is to get you to be able to present information concisely and in a clear manner. So images or pictures, we often say, can tell 1,000 words. So sometimes using an image can be more useful than just tables and tables of data. So we can have tables which summarise data into particular patterns. We can have graphs such as line graphs here, and we'll have a look at a few other versions on the next slide. So for our BPA investigation, that's looking at the presence of an unwanted plastic monomer in water stored in plastic bottles. Here we've got a calibration curve, which is a line graph, and here we've got readings that are taken to interpolate from a calibration graph. Here we have a table of data. Now, while our sample poster shows both, it's probably better to just use one form of information because that saves you space and time. Other ways to present data are bar charts, which are good for categorical data, or schematic diagrams. In this case, we've got the sulfur cycle, or flowcharts. Lots of ways of presenting information with using few words, but using visual things to help. Okay, so to summarise, there are different types of data that you can gather, collate and record during your investigation. Make sure everything is recorded in your logbook. It's the primary source of your whole investigation. Use an example of any worked calculations for any processed data, such as average concordant data. Do that in your logbook. Note down any source of secondary data that you use, for example, the VCA data book or your textbook. And where you can, try and present the data visually as a table, a line graph, a bar graph, a schematic diagram or a flowchart. You can then use that visual image in your report or your scientific poster. The other advantage is it will save you lots of words, and normally you have a word limit of 600 words. Okay, what's coming next is Data and Investigation Methods Part 1. Great, see you then. Bye.